Hello, this is Project MyoArm. Our initiative is to design a system to control a robotic prosthetic arm capable of precise movement, driven by muscular contraction. The group is made up of Jeremy Thompson, Joshua Luke Ware, Kyle Peavy, and Scott Stoller, all students of the Texas A&M Electrical and Computer Engineering Department. Modern arm and hand replacements are either a solid representation of a human hand or a hook-like appendage. These inexpensive devices serve very little functional purpose other than to fill the space of a missing limb. The hook prosthesis is controlled by a cable attached to the shoulder that opens the hook when the shoulder is raised. The alternative is a next-generation robotic prosthetic, such as the iLimb Pulse, a $40,000 limb replacement system with multiple finger configurations that can be changed with the flexing of an amputee's remaining muscle tissue. This system, like the one proposed by Project MyoArm, makes use of surface electromyography. Surface electromyography is the process of obtaining electrical voltage signals from muscle tissue through adhesive, non-invasive electrodes. As the arm muscle is flexed, electrical signals from the brain travel across nerves on the surface of the muscle tissue, telling it to release a variety of chemical elements. It is these chemical elements that cause the muscle to contract. When the arm is relaxed, the brain sends a similar signal, telling the arm to drain these chemicals, causing the muscle to relax. Even after arm amputation, these signals are still sent to whatever remains of arm muscle when the amputee attempts to control an arm that is no longer there, also known as phantom limb syndrome. A robotic arm can respond to these electrical signals much like a human arm. Surface electromyography allows us to pick up these electrical signals through electrodes attached to the surface of the skin. Although these signals are very small, they can be amplified, filtered, and used as input to a robotic arm, telling it when and how to move. The goal of the Project MyoArm is to buy an inexpensive robotic arm, the Linux Motion AL5A, and control its movements solely via muscle flexion obtained from the user's bicep and forearm muscle. This will provide a relatively inexpensive robotic prosthetic to amputees that has a lot of the same functionality as the state-of-the-art technology, such as picking up small objects and gesturing. In addition, Project MyoArm will provide haptic feedback to the user utilizing pressure sensors on the robotic grasper. Our design is comprised of 4 major stages. Stage 1 is the electrodes. First, the area of the arm above the muscle must be clean and free of hair. The medical-grade electrodes are applied to the skin using conductive gel. They are then able to detect a small voltage pulse, approximately 5 millivolts, from a flexed muscle. Stage 2, the circuitry. The signal travels from the electrode leads to a printed circuit board. Here, electrical noise is minimized, and small voltage signal is amplified to around a 5-volt signal during the full flexion. Stage 3, the Arduino microcontroller. The output of the printed circuit board is fed to an Arduino microcontroller, a popular programmable processing board. Our software, downloaded to the Arduino, constantly checks the incoming voltage signal. The Arduino controls the robotic arm joints, also called servos. Servos are DC motors that provide the Arduino with position control. For example, if the forearm muscle is clenched, as occurs when you try to grip something, the Arduino will receive a 5-volt signal from the forearm electrode and output a signal to the grasper of the robotic arm, telling it to close. Project MyoArm has also successfully controlled another joint of the robotic arm from flexion of the bicep muscle. When the Arduino detects a voltage pulse of more than 2.5 volts in the bicep, it shifts the servo motor of joint 1 by 5 degrees. Thus the arm can be cycled through angle positions until the desired position is obtained. If the pulse is held for a significant length of time, such as approximately 1.5 seconds in our program, the Arduino will reset the angle of joint 1 to 0 degrees. Stage 4. Haptic feedback. The term haptic feedback means using sensors to observe the environment and using that information as another input to the system. When trying to pick up something, the nerves in our fingers tell us when we have touched the object and when we have enough force to lift it. In Project MyoArm, we use pressure pads on the grasper to detect when the closing arm has made contact with an object that will be picked up. When the observed pressure reaches a programmed threshold, the grasper will hold its position. and the object between its pinchers, so long as the forearm muscle is still clenched. In addition, when contact has been made with an object, a vibration motor attached to the arm is activated. Here we are showing the flexing of the bicep and its incremental step size of 5 degrees every time it receives a flexing signal, and a reset after a 1.5 flex. Also, the flexing of the forearm causes the grasper to contract. As you can see in between there are the force sensor pads. When I put my finger in the way, it actually stops on there once the force is experienced. To the left, we have the PC controlling the other 3 degrees of motion, up, down, left, right for each of the joints, and then a base rotation of left and right, showing that everything can coincide together. In addition, prototype has also been included, using the Edge robotic arm by OWI. This is the mobile platform. The grasper of this robotic arm is the only active element driven by muscle flexion. The target of this platform is amputations that occur below the elbow. Therefore, the required prosthetic only needs a grasping element to provide the missing functionality of a hand. While the Lynx Motion AL5A is intended to show proof of concept for driving multiple joints of a complete arm replacement, the mobile platform shows that our system could be attached to an amputated forearm and powered completely by battery. For demonstration purposes, the arm is strapped to a non-amputee user by a wrist brace. In conclusion, this device is aimed to increase the quality of life of upper limb amputees by providing an open source alternative. Thank you for your time, and Giga Maggies.